left off is we have an input to a system, beta 0 cosine omega t. We have a response function that's just a pure exponential from dynamics x dot of t is equal to beta of t minus alpha x of t. So a simple one-parameter model for how a cell behaves in response to an input. And then our output was beta 0 over the square root of alpha squared plus omega squared cosine of omega t minus the inverse tangent of, was it alpha over omega over alpha, omega over alpha. Okay. And so now what we'll look at is a paper. Yeah.
Could you turn on the lights?
Yes, I can turn on the lights. There.
Thanks.
You're welcome. All right. So then what we'd like to do is do an experiment to test this idea. Let me move this up a little bit. Where we have the signal omega, and without worrying about the phase shift, we could just think about, so this part, the amplitude, or if we divided by beta 0, the gain, the amplitude gain, that for zero frequency, so here is zero frequency, we expect to get some maximum value. So here, the maximum value would be 1 over alpha. And then as we increase omega, we would expect to see some sort of behavior like this. And when omega is exactly equal to alpha, we would have 1 over, so when omega is equal to alpha, we would get 1 over the square root of 2 alpha squared. So that is 1 over the square root of 2 times 1 over alpha. So that 1 over square root of 2 is about something like 0.7 divided by alpha. So when we are about 70%, we could read across and then figure out what alpha is. So the reason why we can't get alpha from the intercept on the y-axis is because there's this overall scaling of beta 0, which includes effective parameters like the total number of signaling proteins and the activation rate and other factors. So we usually will think about measuring this in arbitrary units and then sort of normalizing to the maximum response. But then in the frequency domain, then we can figure out what frequency the system is responding at. And so what we would do experimentally is collect data and see whether our data sort of follows this model, or maybe our model is completely wrong and the data points don't follow the model. So this is looking at the amplitude of response. We could do a similar experiment and look at the phase shift of the output versus the input. Oh, where's the?
Over here.
Oh, here, yes.
So why is the max at frequency 0, 1 over alpha instead of beta naught over alpha?
Oh, I'm taking out the beta naught. That's just an overall scaling. Yeah, so really, that could, so it depends whether you're dividing by the amplitude that you're sending in or not. So here, you could also do an experiment where you where here as a function of omega, so this is the amplitude again. So here you could do one experiment, say, where the input is beta 0 cosine omega t. And then you can do another experiment where the input is 2 beta 0 cosine omega t. And then you'd want to see that you have a 2x difference in the output if you're measuring the output. So beta 0 cosine omega t, you'd expect this to go to beta 0 over alpha, and here 2 beta 0 over alpha. So we could also check to see that the response is linear over a range of frequencies. All right, so now we will look at the paper together that we will be able to understand now that we've done all the work. So, here goes. How did office hours work yesterday? Was there enough room?
I think we were fine.
All right.
Like 5 people showed up, so.
Okay. Let's see. Where's the computer? There we go. All right. All right, so as a reminder, here's what the system looks like. So here are the cells with a square wave or a sine wave input, and we're not seeing the trace of the input, so we're not seeing the oscilloscope trace, but we're seeing the output. So I'll get back. And now here's the paper. So full text, figures. So we'll go one by one through the figures. All right, and now let's zoom in. All right, so here's the first figure showing what is going on. So osmotic pressure affects the conformation of receptors on the surface of a yeast cell. So these are sensors. And then there are 3 different MAP kinases. So MAP stands for mitogen activated protein kinase. So there's a series of 3 different events where the receptor phosphorylates one of these MAP kinases to tell it should go from the inactive to the active state. And then once this MAP kinase is active, then it activates the next one, and then the next one. And phosphorylation lets this protein go into the nucleus, and that results in glycerol production. So the yeast cell makes antifreeze in order to balance its osmotic pressure with the environment, to prevent it either from, so here it's higher osmotic pressure, so to prevent all of its water from leaving the cell. So here, this sort of shows that they think that they're going to model it as a cascade where maybe there are two different receptors on the surface of the cell that respond to this input that then feed into the same downstream signaling pathway and result in response. And we're going to, so after we finish looking at this paper, we're going to improve our model by seeing what we get with a cascade. Then in C, figure C is sort of the idealized response. So I think for low frequency and high frequency input, and they're sort of an idealized response from the model. So let's see. So what does it say about so C, steady state level, D, oscillating. All right. So X3, so it's a model for, I think, this one. Okay. So that's the first figure. So this figure, this part of the figure is just what we drew. Over here for the amplitude as a function of the frequency input. Here, the reason why this doesn't look like a sine wave, why this looks like there's a sharp point here and a sharp point here, is because this is the output for a square wave input as opposed to a sine wave input. So they decided to use a square wave because they didn't have the good sense to use a sine wave where everything is analytic. And also, since it's a square wave instead of a sine wave, like the phase shift doesn't come through as nicely. So they should have, maybe it was hard experimentally to get a sine wave, actually. To get it was easier experimentally to have a square wave input than a sine wave input. So there's a question in the back.
How would so if you go back to like the graph.
Oh, actually, let me turn off the lights. Nobody fall asleep. Stage front. I'm not sure where the lights for the rest of the room are. Oh well, that's okay. All right, yes?
In the graph that you drew for the frequency domain, how does the phase shift factor into that? Like,
It doesn't.
Oh, it
They separate. So we could do a separate, so if they had been able experimentally to have a sine wave input. So remember, the way that they're getting their input is they have two fluids flowing together, like meeting in a Y-type tube. And depending on pressure, they can change the fluid in the tube to be mostly like port 1 versus mostly port 2. And that gives them the ability to apply a square wave. And probably if they worked really hard to calibrate it, they could apply a sine wave. But
I'm talking about for the graph that we drew on the board.
here?
Yeah. How would the phase, like, how would that phase?
Oh,
phase shift, like,
so here's how it would work. So I'll do it on the side again. Where did I put my chalk? There it is. Okay. So I'll erase this. So there's the output. So we can look separately at the gain and the phase shift. Since that's covering that, we'll show on one side the amplitude. So the amplitude, we start at beta 0 over alpha. And then theoretically, it should look something like this, where at 0.7 or so, this is alpha, and this is the omega axis. So amplitude as a function of omega. So here, I should say amplitude as the title. All right. And then, actually, we'll do this again. And then if we look at the phase shift, So the amplitude is beta 0 over the square root of alpha squared plus omega squared. The phase shift is going to be inverse tangent of omega over alpha. So we'll use this as the omega axis again. And let's put in a couple points. So for omega equals 0, so I'm going to call this phi just so I have a shorthand way of writing it. Phi is equal to the inverse tangent of 0, which is 0. For omega equals alpha, phi is going to equal the inverse tangent of 1, which is pi over 4. And for omega much bigger than alpha, phi is equal to the inverse tangent of infinity, which is pi over 2. And I think it looks like this. So here's pi over 2, here's 0, there is alpha. I think it should look like this. Although I'm not so sure here whether it goes up linearly and then has an asymptote or whether it goes up like this. I think it goes up like that, but I'm not actually so sure. I'd have to work it through, and it's not so important. So you're saying you think it goes like this? Actually, probably it does. So here, I think maybe it goes like this. Maybe that's how it goes. So if I really wanted to, I would write tangent as sine over cosine, and then expand sine and cosine as x squared and x. Anyway, there we go. So probably like that. Maybe. Actually, yeah, probably like that, because sine goes linearly with x at small x. So that must mean that it has a slope through x equals 0. All right. Okay. So the question, I answered the question eventually, right? Okay. All right. So now we'll go to figure 2. Figure 2. So open a new window. So here is figure 2. And so this is showing how the system works. So here is here's a close-up of the cells are sitting here, and there's a red fluid and a blue fluid that are going in. And by changing the pressure, either the cell is filled mostly with red or mostly with blue fluid. And then this is just the mechanics to get everything going through. And then they have a microscope focused. And here what they're doing is across the flow cell, they are imaging what the concentration is. So the way this is done is they just add a dye to one of the fluids that I guess is fluorescent or imageable, and they're able to see from the color what is inside the flow cell. So this isn't looking at the yeast cells, I think. This is just looking to check to see that they can reliably switch back between high osmotic pressure and low osmotic pressure input. And then this is the same, but for faster switching. So here, this is the x-axis, and then going up is the time axis. So they're imaging across the well. And you can see that it's not like on the edges, it's not perfect. So on the edges, even if this is high pressure, this will still be mostly low pressure. But they're trying to convince you that if you're looking in the very center of the flow cell, you're switching back with what looks like a square wave. And then this is different periods, and let's see what they're. So we'll look at signal panel. I'll look at the last panel. All right, C, fluorescence intensity. for a particular point in the middle shown for oscillation periods. All right. Okay. So what they're doing here is they're looking. So they're looking at what the input is in the middle of a cell for different switching frequencies. So they say that for switching frequencies faster than a period of half a second, they're sort of losing the ability to switch rapidly enough, like the fluid's not getting replaced. So they're very comfortable, though, that as they get to longer periods, that the switching looks more and more like a square wave. I mean, here still you can analyze the output for an input like that. There's not. They just. It's further from their theoretical goal of having a square wave. And the reason why, so even though this period is 8 times longer than this period, why all the oscillations line up is they're plotting it not versus time, but versus omega t. So omega t equals 2 pi should be 1 full period. Maybe that's not omega t. Maybe it's supposed to be omega t. Yeah. So it puzzles me why this peak isn't at why it's at 1 point something as opposed to 2 pi, which would be 6. So maybe they have a typo there. All right, figure 3. So figure 3 is finally the data. So here we go to figure 3. All right. Ugh. Oh, okay. So figure 3 are the results looking at the, so this is the system output in arbitrary units, probably the most common units used in biological papers. So they're just, measuring the output and whatever it is, it is. And they have data plotted for wild type cells. And for cells where they've deleted 2 of the proteins that are important in this pathway. And what they see is that regardless of, I'm not sure exactly, we'd have to look back at the pathway map why it's okay to delete these. But what you see is that all of these points sort of fall together. So we're looking over 3 orders of magnitude for frequency input. So 0.1 hertz, that is 10, 0.1 hertz, 0.1 per second. So that's 1 every 10 second. And 0.001 hertz. So that is 1 every 1,000 seconds. So 1,000 seconds is like 1 every 16 minutes. So here, this is a 16-minute switching square wave. Here, this is a 5 or 10 second switching square wave. And you can see that it pretty much follows a functional form like this for the amplitude. So a theoretical model that says that there's one kinase that's being switched back and forth does a reasonably good job of fitting the data. So I think they used a slightly more complicated functional form to get this line through. But if you look at the scatter of the points, I think really a 1-parameter model would be probably fine. So now we'll look at what these different curves are. We have to go down to the figure legend. So figure A is so they're deleting one or the other branch of the pathway. B is a different deletion unit. D. Let's see, what is C? So what they're doing in this figure is they're seeing that what happens when you turn off one side of the pathway is one sort of has a slightly faster response than the other. So there's not so much new there that we didn't see before. And it looks like this doesn't have results of experiments where they increase the amplitude of the input and see you get a linear response. So then for the supplemental information, let's see. So this is an example showing that with a longer period, so with a slower input, you get a higher amplitude response, and then for a faster period, you get a lower amplitude response. So these amplitudes are the data that they're plotting to get the curve of amplitude versus frequency. That one. Haploid versus diploid cells. So that's not some different inputs. The movie we saw, where everything came from, and that's it for the supplement. So let's go back to the main paper now. So we'll look at their equations. All right, so now the equations look very similar to what we were doing. So the reason why this is in the denominator is because they're going to be a little more careful in worrying about saturation. So this output has terms like 1 over 1 plus I omega t. So these are like our terms of, what was it? It was omega minus I alpha, or alpha minus I omega, and alpha plus I omega. So and then the output, so classic low pass filter form. So this is exactly the form that we have of, except that tau, their tau is our 1 over alpha. And so if you multiply by alpha on the top and the bottom, you would get alpha squared over alpha squared plus omega squared, and alpha squared is just a constant. So even though their model looks a little more complicated, they write it as an effective one-parameter model. So they're using the same one-parameter fit that we've derived from having a single kinase that's being activated and deactivated. So I think that's all that we have with this paper. All right. So any questions about response to an oscillating input?
On the biological side of things.
On the what side?
On the biological aspect of it. We're talking about a 3-tier system that behaves as if we're just one kinase. Would there be any benefit, again, I'm asking purely from the biological standpoint now.
So it seems like to the biological benefit of why is it a 3-tier system instead of 1-tier. So we're going to do that by looking at how the output from a cascade differs from the output of a single level. There are two. So there are two reasons that we'll see. One is that you can get signal amplification. So like each level, you can get a little bit more gain, to make a small signal into a big signal. The other question for this paper, what they were looking at is from the biology, they know there are two different inputs feeding into the system. Why does the cell want two different receptors as opposed to just one receptor? And the answer they come to is it seems like the two have slightly different frequency responses. Like one is a little faster responding, one is a little slower responding. So slower to turn on also means slower to turn off. So it could be that a cell wants to do something different if it thinks that it's going to be in a high osmotic pressure environment for a longer time versus a shorter time. So I think that's the conclusion of this paper. So where this type of work is going is that now there are a lot of people doing these types of studies, but in human cells as opposed to yeast cells, looking at pathway elements that are important for cell decision making for, say, proliferative cells in cancer or disseminating cells, other types of cell phenotypes. So there's a lot of work trying to figure out what's going on. And it's still a standard pattern of you look at a wild type cell, you measure its response, and then if you have a hypothesis for the genes that are important, you do some genetic engineering to make mutants in the different proteins that you think are relevant, and then compare the mutant output to the wild type output to see whether your hypothesis about how everything is connected is correct. Yes?
Can you talk about some of our conclusions, like in the context of switch-like response?
Switch-like response. Oh, so here actually we don't we don't really have such switch-like response. Switch-like response is we look at one of these first. So here's the first picture. All right. So actually, another hypothesis about the reason that you have cascades is there's the possibility of getting a more switch-like response. Here, this response is really not so switch-like. It's it's more like a dimmer going from a high state to a low state. Even though it looks sharp, remember that this is a log scale x-axis. So this response sort of happens over 2 orders of magnitude. It's probably tuned to the time scale that yeast actually feels in the wild for osmotic pressure changes. Like in yeast in the wild, they're not going to be super fast oscillations in osmotic pressure. So there's no point for the yeast to have a system that's designed to respond to super fast changes in osmotic pressure. It's more like a yeast cell maybe gets washed off the surface of a grape on, growing out in the fields, and then lands on the ground, and eventually it'll be in a little more high salinity or low salinity environment. So it doesn't need to be fast response, and it also, like switch-like, there's not really so much evolutionary pressure, apparently. So switch-like response often happens later in the pathway at the point of transcription. So we'll talk about switch-like response more when we get to nonlinear systems. So linear systems don't really switch. They change smoothly. All right. Okay. So while we're on the screen, so I have a question. So I just finished this novel, but it's a web novel, so it's like only. So has anyone else taken the time to read this? You like it? I really liked it. Pretty good. So it's a recommendation. Yeah. So my daughter told me I should read it, and she has pretty good taste. So yeah. So I just started Pact now. I'm not sure that it's as good, but I heard Twig is better.
They're all good.
They're all good. Okay. This one was really good. I really enjoyed it. So just, no spoilers. Okay. So here we go. All right. So really, only one person read it? I thought there'd be. What is it about? I don't want to ruin it by saying it. Well, the title is Worm Parahumans, so it's about parahumans. What can I say? But that's.
Are they aliens or like?
I'm not. Look, it's so good. I really enjoyed it. So no more. So yeah. And then she spends the rest of her time watching Supernatural. So is it like anyone watch Supernatural? A little, like no one wants to admit it though. So that I don't have time for. All right, so now okay, so now we're going to do the cascade to show that the generalization to a cascade is really pretty easy. So I just want to make sure I use the same notation as in the notes. So we have a cascade where one kinase activates the next kinase in a pathway. And in the MAP kinase cascade, usually there are 3 in a row, maybe with the receptor on top. And we'll write the dynamics. So x1 dot of t is equal to k1 beta of t minus alpha x1 of t. X2 dot of t is equal to k2 x1 of t minus alpha 2 x2 of t, and it goes on for n steps. So xn dot of t is equal to kn xn minus 1 of t minus alpha n xn of t. So that is our n-step cascade. And you notice I've written each will have a different activation rate and a different deactivation rate. Although for some analysis, we'll make it easy on ourselves and say all those rates are the same. And unlike our previous, so when you're just thinking about one level, we just call the input beta of t. Here we're going to add in a k1 beta of t just so that every level has the same form. So now we'll solve it. So s x1 twiddle of s minus x1 at time 0 is equal to k1 beta twiddle of s minus alpha 1 x1 of s. And we'll assume that at time 0 the system is off. So we know that we can get transients if we want that include relaxation from the time 0 state, but we'll just assume the system is off at time 0. So we get x1 of s is equal to k1 over S plus alpha 1 times the input. And then similarly, for the second step, we get S plus alpha, well, I'll just write it like this. We get x2 total of S is equal to 1 over, or K2 over S plus alpha 2 x1. So we're assuming that x1 at time 0 and x2 at time 0 all 0. So we get x2 in terms of x1. And then we can replace the expression for x1. So we get k1, k2 divided by s plus alpha 1, s plus alpha 2 times the input. And then if we finally get all the way down to xn, you can just sort of see the pattern. We get a product of all of the response functions for the individual layers times the input. So a very simple form. And if we want to think about what the time domain output is, it's a real pain when these alphas are all different. So when the alphas are all different, like you can imagine if you did the inverse Laplace transform, you would get a series of exponentials. So there would be n separate exponential terms that we would add up. So instead, to make it easy, we'll make an approximation for the time domain that all the frequencies are the same. All right, and now our question is, what does the time domain output look like? And we could also ask, what is the gain? And what is sort of the signaling width? So we'll start looking at the time domain. So xn of t is equal to ds over 2 pi I minus I infinity to I infinity of k to the n. What did I want to do here? I want to do a beta, yeah, response function. All right. So this is equal, we could call this hn of s, beta of s. So really, we're going to just focus on the system response function. So what is the response function in the time domain? So to get the response function in the time domain, we do the inverse transform. And now we don't have a simple pole in the denominator. We have n factors of s plus alpha in the denominator. And if you remember back, the way that we deal with this is we can do a power series expansion of the numerator in powers of s plus alpha, and then just pick out the one term that gives us a 1 over s plus alpha in the end. So we can write e to the st as e to the s plus alpha times t e to the minus alpha t. So we're multiplying by 1 in the form of e to the alpha t times e to the minus alpha t. But writing it this way lets us do a power series expansion. So this is equal to the sum from, so now I need an index variable. I don't want to use n because we've already used it in k. And J, oh, look, yeah, J looks too much like I. Say L. Actually, L is bad because when you write that, so say M. 0 to infinity, S plus alpha to the M, T to the M over M factorial. And we have, so for term M, we'll have an S plus alpha to the M in the numerator and an S plus alpha to the N in the denominator. So the only term that contributes in the end to the integral is M is equal to N minus 1. So when M is equal to N minus 1, then we'll get an S plus alpha to the N minus 1 divided by S plus alpha to the N, and then we can do that integral. So all the other terms in the power series are there, but when we do the contour integral, they all go away, except for this single term. And so the result is that Hn of t is equal to k to the n, and then e to the minus alpha t. So that's that e to the minus alpha t that we got. And then t to the n minus 1 divided by n minus 1 factorial. And we can check that when we have a one-level cascade, this agrees with our previous answer. So for a one-level cascade, we expect to get a response function of e to the minus alpha t. So for n equals 1, there's the e to the minus alpha t, t to the 0 is 1, 0 factorial is 1. We have the factor of k in front that we didn't have before because we changed our definition of the model to have this k multiplying beta. So before we just had beta as the input. Now we have k times beta, and so that k shows up in the response function. So, so what that looks like is, if we think about, so this k to the n over n minus 1 factorial, that's just that's a prefactor that we'll leave to the side for now. We have an exponentially decaying function, so e to the minus alpha t, and then we have a growing function, t to the n minus 1. And so they're fighting it out. So this one is getting bigger while this one is getting smaller. So we know that exponentials win out over algebraic powers. So as t goes to infinity, it'll go to 0. At t equals 0, this term is 0 as long as n is bigger than 1. So here, this is t. So if we look at what we get when we multiply the two, in the end, the response function looks like something like this. So this is going to be Hn of t, something like that. So I didn't draw it exactly right, but it'll look something like that. So a bit like, say, a gamma function. Actually, it's the integrand for a gamma function. So gamma distribution is what it is typically called. It's sort of the continuous the continuous analog of a Poisson distribution. So you're familiar with Poisson distributions that have a peak, start at 0, and then have a tail. So so that's typically sort of what it looks like. And we'll think about the time that it has its maximum value. So at what time, say Tn, does it have its maximum value? And we could also think about the amplitude. All right, so the maximum value. When does it have its maximum? Erase that. So the maximum value. So that's so the argmax of Hn of t. So what we want is that ddt of Hn of t is equal to 0. And usually it's easier to do these things on a log scale. So when a function has an exponential, it's easier to take the log first before you take derivatives. So we can, as long as hn is bigger than 0, we can multiply on both sides by 1 over hn of t. And then 1 over hn ddt of hn of t is the same as ddt log n of hn of t. So when the derivative of the log is 0, the derivative of the function itself is 0. So we have, this should be 0. So this is ddt of the log of, what is it, e to the minus alpha t, t to the n minus 1, and then it was something like k to the n over n minus 1 factorial. So we're taking the derivative with respect to t of the log of this, and so that's equal to the log of e to the minus alpha t plus the log of t to the n minus 1 plus the log of k to the n over n minus 1 factorial. But this factor doesn't have any power of t in it. It's affecting the height, but it's not affecting the position of the maximum. So we can ignore that. So 0 is equal to ddt of minus alpha t plus n minus 1 log t. Erase some more. So this is equal to minus alpha plus n minus 1 over t. So the time that the response function has its maximum value is equal to n minus 1 over alpha. So we keep seeing the single parameter alpha show up. Alpha is the deactivation, the time it takes for each level to deactivate, and that sets the time scale of our system. So the activation rate, so k, the rate to activate ends up affecting primarily the gain, not anything having to do with time scales. So this is a little confusing at first, because say that you want a system to run faster, a signaling pathway to run faster. We have 2 states for each level. So we have the inactive state and the active state. So this rate is alpha. This rate is k times our input, say. And we might think that if we want everything to run faster, we should increase the rate of this step. But it turns out almost always the way things run faster is you increase the rate of deactivating the system, and that's what controls the time scale. The activation rate ends up mostly affecting the gain, not the time scale.
So decreasing alpha means?
So increasing alpha, increasing the deactivation rate, increases the rate of the pathway overall. So that's like, or you can think about the time it takes to deactivate. So the time that it takes to reset the system tells you how quickly the system can respond. So we've calculated the time of maximum response. We could next calculate the amplitude or the gain by substituting that time back into the response function and seeing what you get. That gets messy pretty quickly. So we're not going to do that, even though that's in the notes. Instead, we'll calculate things that are much easier to calculate. So we've calculated the time of max response, but instead of thinking about calculating the amplitude at the maximum response, instead we'll think about the total integrated response. So the idea is that, so here's t, and here is the system response. say that our input is a delta function. So input is equal to beta 0 delta of t. Our output is going to be beta 0 h of t. And in general, for any input, so for any input beta of t, our output is equal to, so the total output is equal to 0 to infinity dt, 0 to dt prime, h of t minus t prime, beta of t prime. So something like that. All right. So so what we're calculating often is called the area under the curve. So the idea is the area under the curve for the input is equal to 0 to infinity dt beta of t. So that's equal to the limit as s goes to 0, 0 to infinity dt e to the minus st of beta of t. Which is the limit as s goes to 0 of beta tilde of s. So the reason why the limit as s goes to 0 is in there is because for some functions that will be a finite number. So for example, a delta function input will be integrated to the total area. But for other functions that we might use, other inputs we might use, it will be it will diverge. So for example, for a step function, if we integrate a step function to infinity, it'll go to infinity. So so that's why we have the limit there. In the end, it doesn't really matter. We saw before we could always add some sort of long-term turning off of the signal. So the AUC of the output is equal to the same way. It's the limit as s goes to 0 of x of s. Where here, this is the output we're measuring. So for us, it's the output at the end of the cascade. So that's the limit as s goes to 0 of h of s beta of s. And then we can calculate the gain. We'll just define the gain. So the AUC gain is equal to the AUC output divided by the input. So it is limit as s goes to 0 of h tilde of s beta of s divided by beta of s. Those cancel. And so it is h of s evaluated at s equals 0. And we no longer have to write it as the limit because the response function should be finite when we integrate it. So imagine that we had a response function that wasn't finite. That would mean that you could hit the system with a finite input and you would get an infinite output. So that doesn't happen for real systems. Maybe for an ideal perfect spring you would get something like that. But for the systems that we'll talk about, it doesn't happen. And so we can just evaluate it at 0. So this is the gain. And now you'll see this is much simpler to calculate than than the amplitude gain, where first we have to calculate the time of maximum output and then substitute that back in and get a messy expression. Here we just calculate the gain by setting s equal to 0. So in the response function. So, and it doesn't matter what the input is because we have a linear system. So for our cascade, so where was h? So here's h. So h of t is equal to k to the n over s plus alpha to the n. So the AUC gain is just equal to k over alpha to the n, because we set s equal to 0. So that is a much simpler calculation than worrying about it in the time domain. When we look at integrated properties, they're much easier to calculate. So essentially, we get a gain of k over alpha for each step in the cascade, and then they multiply. And also, to do things in the time domain, in order to be able to do it on the board, we had to assume that all of the steps had the identical parameters. But in fact, for an actual system where there might be different parameters at each level in the cascade, so really h of t should be the product j equals 1 to n kj over s plus alpha j. Then our gain, so often we use capital G for gain, is just the product of kj over alpha j. So it's easy to calculate when we have a system where not everything is the same from level to level. So I think as a homework problem, I think as one of the homeworks, you'll see, so one of the homeworks I think has you apply a cosine input to a cascade possibly, so I don't remember whether that's still one of the inputs, but you'll end up proving that for a cascade, if the input is something like beta 0 cosine omega t, the output is very simple. It's beta 0 times the product over j of, I think, kj over square root of alpha j squared plus omega squared. So the product of all the terms that we had before, one for each level, and then cosine of omega t plus the sum over j of the phase shift for that level. So the phase shifts add and the gains multiply. Yes?
So you mean h of s, right? Because
yes, h of s. This should be h of s. That's right. All right. So that's the AUC. So that tells us when we integrate the input and integrate the output, how much bigger is the output than the input. So like gain means we're gaining something. It could also be smaller. It could be that we have a cascade that sort of moves a signal down in strength. But it depends on the ratio of the activation to the deactivation step. If the activation rate is bigger than the deactivation rate, we have gain at each level. If it's smaller, then we have loss at each level. So that's the first thing that we're going to characterize. So the next thing that we're going to characterize is the time of response. So we've calculated the ratio of the output area to the input area, but we don't know when the output happens. And we saw that for the cascade, each time we add a level to the cascade, we sort of have a delay to where the maximum is. So for these integrated properties, we're not going to think about the maximum, the time where the output has a maximum. We'll think about the mean time of response. So for an input say that we have an input beta of t to make it meaningful that's greater than or equal to 0, all right, for all times. So what is the mean time of the input? So I'll call it, in the notes, calling it t bar. So the way that we're going to define it is we integrate over all time beta of t times t, and then normalize it by the strength of the input at that time. So just a weighted average of time where time is weighted by the input. So if you thought about, instead of thinking about beta of t as an input, if you thought about it as a probability distribution, say, over time, where, here's the probability of random variable t, the way that you would calculate the mean of a probability distribution is you sum up t times the weight at that time and then divide by the total area as a normalization. So it's like you're figuring out where you put the time that if you cut out this area, it would exactly balance. So that the area to the left is equal to the area to the right. So that's the mean. All right. So I think it is very easy to calculate this from Laplace transforms, and we will do the proof of how you do it at the next lecture. So we're done for today.